We're now going to look at the free response of a parallel RLC circuit. And in this circuit, we have the resistor, inductor, and capacitor that have been attached to a voltage supply through a 4 ohm resistor, and it's been attached this way for a long period of time. And then at some instant, we're going to open up this switch and see what happens to the system. And in this case, we're interested in determining the voltage or the potential that's developed across this parallel combination of R, L, and C. So we need to develop our differential equation model so that we can solve this second order system. We know that it's a second order system because we have an inductor and a capacitor, or we have 2 energy storage elements in the system. Alright, so the circuit that we're interested in coming up with the differential equation for after that switch is open is just the parallel combination of R, L, and C. Okay, I want to point out here that if we're when we're going to be looking at our initial conditions, it's going to be handy. We can make a source transformation here. We can apply a source transformation to turn this 4 volt in series with a 4 ohm resistor into a 1 amp current supply in parallel with a 4 ohm resistor. And that will come in handy in a little bit, but I just wanted to point out that our source transformations that we've done previously with purely resistive circuits are still valid and still apply here. Okay, so we're interested in determining the output voltage across the resistor, inductor, and capacitor as a function of time. Since we're trying to determine how the potential is going to change, since we're looking for a voltage, we probably want to try to start off by using the node voltage method. Alright, and we have 2 nodes of interest right here. We have this top node and we have this bottom junction between all of the elements. And I'm going to call that bottom junction our 0 voltage reference junction. And I'm going to perform my Kirchhoff's current law balance for this top node. And Kirchhoff's law tells us that the current through the resistor plus the current through the inductor plus the current through the capacitor has to sum to 0. Right, I'm going to come down here and now apply the current to voltage relationships for all of the elements. So for the resistor, it's the voltage or the of interest, or the output voltage, divided by R. For my inductor, my current to voltage relationship is 1 over L times the integral of V dt plus the initial current through the inductor at time 0. And for my capacitor, the relationship for voltage is C dV dt. Alright, remember that this is a free response case, so we're not adding any energy into the system, so we're going to have a homogeneous or free response. Again, I wind up with my integral differential equation that I want to turn into a standard second order differential equation, and I'll take the derivative of everything. When I do that, I wind up with 1 over R dV dt plus 1 over L times V plus C times the second derivative of the voltage, the output voltage with respect to time. And rearranging to get it into a more standard form, I will wind up with RLC times d squared V dt squared plus L dV dt plus R times V equals 0. Alright, again, now that this is in standard form, that's M, that's my damping coefficient, and this is the stiffness of the system. Alright, using those values now, I can determine what type of system response for the second order system that I can expect. And the second order response is given by the damping ratio. So the damping ratio, as we all know, is given from the general form as C over 2 times the square root of Km, which in our case, C is the inductance value, and K times M will give us R squared times LC. which will simplify into 1 over 2r times the square root of L over C. When I evaluate that, when I plug in the given values, I find that the damping ratio is 0.791, and since that's less than 1, we have an underdamped second-order system. Knowing that I have an underdamped second-order system, I know that I will need a couple of other key pieces of information. First of all, I'll need the natural frequency, omega n. Omega n is given as the square root of k over m, which in our case will be r over RLC, which will give us the square root of 1 over LC. And when I plug in values, I get a value for the natural frequency is 3,162.28 radians per second. And I can also compute the damped natural frequency. The damped natural frequency is the natural frequency times the square root of 1 minus the damping ratio squared. And when I compute that value, I get a damped natural frequency of 1,936.49 radians per second. Also, I know that I'll need the product of my damping ratio and my natural frequency, and I can solve that a number of ways, but I wind up with a value of 2,500 radians per second for squiggle omega n product. Okay, now that I know that I have an underdamped second-order system and it's a free response case or a homogeneous case, I know that the general solution is going to take on the form of have some sines and cosines in it as well as exponential functions. For this case, I'm going to use the form of the solution of the unknown coefficient times e raised to the negative squiggle omega n times time times the sine of omega dt plus the phase shift. Alright, so I know from my general solution cases that if I have an underdamped second-order system that's a free response, this is one of the forms that we can use to represent the response. F is an unknown constant, and my phase shift phi is an unknown constant as well. And I can determine those if I can determine the initial conditions for the system. Okay, so what we need to do is we need to determine the initial conditions so that we can solve explicitly for the values of f and phi. Alright, so I'm going to look at the system just before the switch changes position, just before we open that switch. Alright, and I'm going to use the properties of the inductors and capacitors and how they operate in the DC steady state. So when this switch has been closed for a long period of time, I can use my source transformations to represent the 4 volts in series with the 4 ohm resistor as a 1 amp in parallel with a 4 ohm resistor. Now I know that if it's been operating in the DC steady state, my resistors are not going to change their behavior. But I do know that an inductor, since it's been operating in the DC steady state for a long period of time, the magnetic field of the inductor has been fully established, and therefore current is allowed to flow freely through the inductor, and therefore the inductor acts like a wire. And I also know that the capacitor, if it's been operating in the DC steady state for a long period of time, is going to act like an open circuit. So by using these simplifications, I see that just before the switch opens, that I have a short circuit between or across my resistive elements. Because that inductor acts like a wire or a short circuit, all of the current that's being provided by my current supply or by my voltage supply has to pass directly through that wire and not through the resistors. That also means that since the two ends are connected directly, that the potential right before the switch opens across the capacitor has to be 0 as well, because there's no potential difference across a wire. So the output voltage at time 0 is going to be 0 just before the switch opens. Alright, so right after the switch opens, that tells me that we know from the properties of capacitors that the potential across a capacitor cannot change instantaneously. So right after that switch opens, we know that the potential across the capacitor has to be the same as it was right before the switch was opened. So that means there's 0 volts across the capacitor, or 0 volts of potential across all of the elements of the circuit at time is equal to 0. Okay, to determine the derivative initial condition, we're going to go back to the analysis of our circuit right after the switch opens, and we're going to look at our Kirchhoff's current law of balance at time is equal to 0. Alright, so again, right after the switch opens, our circuit is going to look like this. We have R, L, and C. And our current balance at time 0, right after the switch opens, is the current through the resistor plus the current through the inductor plus the current through the capacitor at time 0 has to sum to 0. Okay. We know that we're looking for the derivative initial condition, so we need a dV dt at time 0. And here, the only current to voltage relationship that's going to give us dV dt is the capacitor term. So we're going to be interested in how we're going to use the capacitor relationship here to determine the rate of change of the voltage. So the relationship here is C dV dt at time 0. All right. We've already determined for our resistor, or sorry, we've already determined that just before time is equal to 0, or just before that switch opens, that there's no potential across these resistive elements, and we've also determined that there's no potential the instant that that switch opens. So we know that the relationship for the resistor for the potential is V over R, but we've determined that at time equals 0, this voltage across the resistor is 0, so that term is actually going to turn into 0. So there's no, since the capacitor can't change the potential across it instantaneously, there's going to be no current flowing through this resistor, this 2 ohm resistor, at time is equal to 0. And that leaves us with how much current is flowing through this system at time equals 0. Alright, so just before the switch opens, the magnetic field of the inductor is fully established, and we before saw that all of the current had to be passing through that inductive element. Knowing from the properties of inductors that the current through an inductor cannot change instantaneously, that means that I at time 0 minus, just before we open the switch, has to be equal to 1 amp. But we also know from the properties of inductors that that current can't change instantaneously, so right after we open the switch, that current through the inductive element also has to be 1 amp. So initially, we have to have 1 amp of current right at the very instant that we open the switch flowing through that inductive element. All right, so this gives us what we need to be able to solve for the rate of change, or our derivative initial condition. So from that, we can establish that dV dt at time 0 has to be equal to negative 1 amp over our capacitance. All right, that's the same thing as negative 1 amp over 100 times 10 to the negative 6 farads, which gives us a value of negative 10,000 volts per second for the rate of change of the potential across all of the elements, all of the parallel elements of the circuit at time equals 0. Alright, so I have my initial condition, and I have my derivative initial condition. I have the form of the underdamped second order free response case. And now I can return to my note packet and look at the general solution that we derived earlier for the underdamped free response case, and I can find the relationships that are going to tell me how to calculate the value of my unknown constant f as well as my phase shift phi. And those depend upon the initial conditions, the derivative initial conditions, the damping ratio, the natural frequency, and the damped natural frequency. Okay, so I know that the value of f is going to be the square root of my, this is going to be the value x naught, the constant x naught, and this is going to be v naught. So I know that the constant f is v naught minus squiggle omega n times x naught divided by the damped natural frequency. I'm going to take that, all of that, and square it and add it to x naught squared. And when I do those calculations, plug it all into my calculator or Excel, I find that the value of f is 5.164 volts. And the value of my phase shift is the inverse tangent of x naught times the damped natural frequency divided by v naught minus squiggle omega n times the initial condition. And when I evaluate that, I get the arctangent. This term right here, because x naught is 0, is going to end up being 0. So the arctangent of 0, we have to remember a little bit of trig here, is going to be a value of pi. Alright, so my phase shift is going to be pi radians. And my constant f is going to be 5.164 volts. I will now plug those values back into my general assumed solution here, and I wind up with the function of time that describes the potential across all of the parallel elements as being 5.164 times e to the negative 2500 t times the sine of 1936.49 times time plus pi. Alright, but I know from trig that sine of anything plus pi is going to make that make the sine the trigonometric sinusoid function negative. So that's going to be the same thing as negative 5.164 e to the negative 2500 t times the sine of 1936.49 t. Okay, so this is the general solution, or the complete solution, that tells me how the potential across the parallel elements, the 2 ohm resistor, the 1 millihenry inductor, and the 100 microfarad capacitor, is going to change as a function of time. Okay, so just to recap, we performed Kirchhoff's current law to determine the governing differential equation and establish using the coefficients and plugging in the values of the coefficients into the damping ratio formula. We found that it was an underdamped system, so we need to expect oscillatory behavior in our solution. We determined the initial conditions by applying the properties of capacitors and inductors both before the switch opened as well as right after, immediately following the switch opening. Based on those initial conditions as well, for the derivative initial condition, we applied Kirchhoff's current law at time equals 0, and used the property of the capacitor to establish what was happening to solve for our derivative initial condition for the voltage. And when we did all of that, we came up with a general solution that did indeed have a sine function with an exponential decay modifying it. So what happens here is that as soon as that switch opens initially, as we determined from our initial conditions, there's no potential across the parallel combination, but there's a significant rate of change of voltage across the elements. So at time equals 0, we start at V equals 0. And then we're going to have a large negative potential that's developed across all of the elements. Then eventually, that energy is going to be dissipated back through the system. It's going to start to slowly, or actually very quickly, reach 0 volts. But as it approaches 0 volts, because it's an underdamped system, it's going to actually overshoot that 0 volt steady state condition and slightly oscillate about 0 volts. But because of the damping ratio, since we have a damping ratio that is closer to 1, the oscillations are going to settle out pretty quickly. All right, and that's what this general equation right here, the solution to this system tells us. We have our sine function, which gives us the oscillatory behavior, and then the exponential function in front gives us that decay in the oscillations.